Why is the weather so hard to predict? Well, it has to do with chaos theory. Let's think. What normally comes to mind at chaos? Disorder, maybe a food fight, right? Well, in math, chaos theory means something different. It explains dynamical systems. Chaos theory generally defines chaos based on two things: small changes with big effects and overlapping effects. Let's first look at small initial changes. This essentially means that a small change in the beginning can lead to big changes in the outcome. A common analogy used to model this is if a butterfly in China flaps its wings, that change can cause a tornado in Texas. In this case, the flapping of the butterfly's wings represents the small change in initial conditions that has big effects. Next, chaos theory requires overlapping effects. Basically, a system evolves over time so that any part of it overlaps with any other given part. Dependence on initial conditions alone isn't chaotic, and an example of this is repeatedly tripling two values. All numbers except for 0 would go towards either infinity or negative infinity. If there are overlapping effects, it's impossible to break the system into two different parts since they're so mixed together. But what exactly is chaos theory useful for? Let's go back to our original question of weather, which is a chaotic system. As Edward Lorenz found out when he was simulating weather, small errors or limited information can grow rapidly in a forecast. The theory can help with the prediction of long-term events such as global warming and the greenhouse effect. It's not just big weather events, though. It can also be used on a more specific basis. Chaotic systems are found in nature, biology, physics, economics, and more. Take, for example, this chaotic equation, which models population growth. It's also been found that traffic flow can follow a chaotic pattern, and this information can be used to help with congestion and mobility. From the swinging of a pendulum to creating ciphers, chaos theory plays a big role in understanding the complex systems of everyday life.